So welcome back from spring break. I hope you are recovered from semester, but you don't have to recover from spring break, depending on what you did. But yeah, we're in for the last burst of the class. And what we have now is a bunch of different specific applications of different optimization techniques that we've been learning, right? So today, last week we talked, right before spring break, we talked about linear programs, right? Today what I'm going to talk about is quadratic programs, which is basically programs that have quadratic objectives, right, instead of the linear objectives. And we'll talk about what makes them special and why we care about them. And then the lecture on Thursday is going to be on second-order cone programs. So those are called SOCPs, SOCPs, whatever you want to call them. I will not be able to give that lecture. I have another meeting at the NSF that I have to attend. So Dhruv Pai, who is a senior TA, has TA'd this class many times. He's a PhD student here at Berkeley. Will be giving the lecture on my behalf. So I will not be here on Thursday. My office hours on Thursday after class will also be canceled. But today I have office hours as usual. So anyone who wants to come talk to me, definitely come talk. Dhruv will not be holding my office hours, but there will be regular office hours with, I believe Jingfeng is there right after. So there will be an office hours, just that I won't be there. So that's announcement number 1. Announcement number 2 is that we have posted the projects online. So we posted a draft version, and now we have a slightly updated draft. None of the technical material has changed, but just some of the logistics, which we hadn't really included in the previous post, are now up. So there are, again, 3 different options for projects. One is on adversarial machine learning, where you're thinking about neural networks and how do you handle classification errors that are made by neural networks in the context of adversarial perturbations. So what does that mean? So if you have, for example, a neural network that is trained to figure out, oh, is this a stop sign or not, right? And you want the neural network to classify this as a stop sign or not. An adversarial perturbation is something that changes some small pixels in an image of a stop sign, but it then looks to the human, right? Like if you take a stop sign, sometimes you're driving around and you have, all kinds of things that people sometimes do graffiti on stop signs, or like there'll be a stop sign and then someone says stop driving, like if you're going around Berkeley, or there'll be different kinds of messages that people will put. And so you don't want your autonomous car to be able to be fooled by something like this, right? Just a small scratch here and there. But turns out that that is what you can do. And this is called an adversarial perturbation on a neural network. And so what the project is about is it's about a paper that develops a technique to be robust to adversarial perturbations. So as long as the perturbation of the original image is not too big, you will basically be able to prove that your neural network will still do the right classification. And this relies on using duality. So that's the main connection. So you're basically going to be computing a dual and using the dual certificate properties to be able to prove that there's nothing that can be done. The second project is about control theory and reinforcement learning. And you will be using techniques such as policy gradient to be able to identify new control strategies for a decades-long open problem in control. So here, what is policy gradient? Well, you've all heard of gradient descent, right? By now, hopefully, everyone knows what gradient descent is. But basically, the idea is that, well, if you're trying to find a minimum of a function, what you can do is that when you're trying to find a control strategy, you can parameterize that control strategy by using some parameter. And then to find the best control strategy, you can think of that as finding the best parameter. And you can use techniques like gradient descent to be able to find that parameter. So that's what the second project is about. All of these projects, I should say, have some component that is theoretical and mathematical, where you have to do some proving of things. and some component that relies on you writing code. Okay? And the third project is about understanding a modification on gradient descent. It's a more theoretical project in that sense. And it has basically, it talks about Nesterov's accelerated gradient descent. So this is a method that can be used to speed up the performance of gradient descent. It's something that for a long time has been considered kind of magic. No one understood how it worked until some recent papers have really kind of brought to light how this works. And so the project is basically going to walk you through how Nesterov's acceleration works, and then there will be some extensions that you can kind of pursue to try and modify things to work even better under certain other circumstances. Okay? So the project logistics have been released. There's a post that went out yesterday with some basic things. If you want to do the project in a group, you can do a project in a group of up to 3 people, but you have to commit to that group in the next week and a half. Okay, so you have a week and a half to find a group, and once you commit to a group, you cannot back out of the project. The project is entirely optional, but it is not okay to say that I'm going to do a project with a group and then the last minute say, actually, we were going to do the project together, but see ya, bye, you're on your own, right? So that behavior will be penalized, and that is why there's a commitment mechanism. Just because the commitment mechanism is a week and a half from now does not mean you should start doing the projects after that, right? The project was released before spring break, so hopefully you've all already read through the first drafts of these and picked kind of what you're most interested in. If you're looking for a group and you can't find one, I strongly recommend posting on the EdStem to see if there's other people who might be interested. If not, hey, you're in lecture every day, look to your left, look to your right, grab someone and say, hey, do you want to do a project together? Okay? The question is, how many hours is the project supposed to take? I have absolutely no idea. It is definitely more than doable in the amount of time that you've been given, but I do not recommend starting it the night before it is due. I think that is a failing strategy for sure. Different people will take different amounts of time, right? It's an open-ended research project. The idea for this is for you to get a sense of what research is like. So there's not a specified solution, right? It's not like a problem set where if you get stuck, you ask a TA and the TA knows the answer. The TA does not know the answer. It's research. So you could be done really fast. It could take forever. The idea for this is for you to get a taste of what open-ended research is actually like. Yes, the project will only help your grade. So we will compute 2 different grades for you in the class. One as though you never did the project, and one as though you did the project. And we will assign you the grade that is the larger of the 2. So it cannot possibly hurt your grade to do the project. There is never any downside. The only thing that might happen is you might learn something. No, the projects are up now. And nothing was, before spring break, we released basically a complete draft, but we didn't have things like the number of people per group fixed, but there's nothing changed in the project. So the projects exactly as they were released before spring break stand.
So the problem statements are finalized?
The problem statements are fully finalized. They were already finalized before spring break.
Okay, thank you.
Okay, so I recommend starting early. People who start at the very last minute tend to regret it, and then there's a long office hour queue, and people get stuck, and then you feel like dropping out of the project. That's not a good way to be. You're not going to get the most out of it. Start now, start early, and there's more than a month for you to kind of get stuff done, okay? So pacing yourself is going to be really important. Every project will be assigned a specific TA to help you with. So these are very involved, very complex projects. So not every TA knows about every project. So you have to go, if you're choosing a particular project, you have to go to office hours for the TA for that specific project, okay? Because this is just we're now completely beyond the realm of what is taught in class, right? This is much more complex material. There's a specific office hour on Tuesday mornings that is dedicated to projects. And that is the one office hour where all 3 projects can be supported. Okay, so we're canceling the Thursday evening office hour, I believe. It was 6 to 8 p.m. And moving that office hour to be Tuesday morning, 10 to 12, so it's not right before the homework deadline, and so that you can come and work on your projects during that time, okay? So start working now. Don't say I didn't tell you. Really recommend starting early, okay? Stuff is always crunching towards the end of the semester. Okay, great. So with that, we're on to talking about QPs. Okay, so basically any optimization problem that is of the form here we will assume H is equal to H transpose is symmetric. Maybe I won't assume the PSD-ness yet. So when I have an optimization problem that is of the following form, maybe I could add a plus D here as well. The objective function here is the generic form of a quadratic vector, right? This is a second order polynomial with vectors, right? Everyone's seen this. So the objective is quadratic and the constraints are linear. This is called a quadratic program. In general, we'll assume that H is equal to H transpose and is symmetric. Now, if I want this to be convex, if I want this to be a convex program, what do I need to have true about this particular quadratic equation or quadratic expression? Right, so what needs to be true about H? Are all quadratic functions convex? No, right? If you just think about the scalar case, if I have ax squared plus bx plus c, for what a's is the quadratic function convex? If a is positive, right, the leading coefficient has to be positive. If the leading coefficient is negative, you have a downwards facing parabola, right? If the leading coefficient is positive, it's going to be an upwards facing parabola. If you want convexity, you need that first coefficient to be positive. The same thing here is that this has to be positive semi-definite, right? So if you want convexity, H must be PSD, okay? So you could have quadratic functions that are not convex, and if they're not convex, does that necessarily mean they're concave? No, right? If this was negative semi-definite, then one could say it was concave, but you might have something that has some positive eigenvalues and some negative eigenvalues, right? That would give you something that looks like a hyperbola, like basically something that looks like a saddle, right? Where you're kind of going up in this direction, but you're going down in this direction, right? So that's called a that could be a hyperbola, and that would be something that is neither convex nor concave. In some dimensions it's convex, in some dimensions it's concave. It really depends on your eigenvalues, right? So you had to check to see the eigenvalues of H to determine if this is a convex program or not. So the nice thing about quadratic programs and why we like them is that in most cases, you can actually solve them explicitly. Okay? So in the case, for example, why do you like quadratic equations, right? Linear equations and quadratic equations in the scalar case are also something that we like. Because if you have a quadratic equation and you want to solve it, well, you have the quadratic formula. Right? In the scalar case, you all know that. And so you can decide very quickly what the solution is. As you get to higher and higher degree polynomials, that doesn't hold. So in the case of quadratic vector equations, we actually have explicit solutions in many cases. So what I'm going to talk about first is the unconstrained QP. Okay? So I have P star is equal to the min x belonging to Rn of, let's say, 1/2 x transpose hx okay? Here again, I'll assume H is symmetric. Oh, so here I'm thinking of C. I should not use C and D because we have C and D over there. I should use f x is equal to g. So I'm just thinking of this as linear equality constraints, right? So your inequality constraints and your equality constraints are both linear, which ensures that this is a convex constraint here, right?
So F is a scalar, right?
F is a matrix. So yeah, I ran out of letters, right? A, B is gone, C is gone, D is gone. E feels like expectation, so I chose F. G does feel like a function, but then H is already gone. I, J are already problematic. So like I just kind of made some compromises in my notation. But F is a matrix. Okay, good. Very good question. So those two C's and D's are not related. I had just, yeah. Okay, good. So but here, this C is a vector. This is a scalar, right? Because now this is all real valued. This is real valued, this is real valued, this is real valued. Okay. So we're going to solve this in cases. And we're going to think of case 1, which is H is PSD, which we write as H greater than or equal to 0. And I'm going to say C belongs to the range of H. Okay? Remember, this is the range of H. So I want to try and solve this quadratic equation. And when we're trying to solve this quadratic equation, in general, when you have, for example, a scalar function, right? If you had a scalar thing, how would you try to figure out what the minimizer of that was? Any strategies on what one might do? If I just had something that looked like this.
0 derivative.
One thing you could do is just take the gradient and set it to 0, right? So that's definitely something that we can do here and try to find the minimizer that way. And that would work perfectly great. What I'm going to try and do is I'm going to show you a different technique that will allow you to kind of build one more tool in your toolbox, right? And for this, what I want to talk about is this idea of completing the square. So when you're trying to minimize a function in general, one thing that can be true is that what if you could write your function as something that's a square or a perfect square or something that you know is going to be non-negative plus something else, right? Then you can always kind of make guarantees about the one thing that's the square. And then you can kind of like break the function up into two things. Okay? And so that's the strategy that we're going to use. So for example, you might have done this in the case of scalar quadratic functions, is you write this as something as like something squared plus something else, right? And so that's what we're going to try and do. So let's say if I call this thing, let me call this f of x. And let's say I want to write, can we write f of x is equal to 1/2 x minus x naught plus some alpha. Okay? So I'm saying, can I choose an x naught and an alpha such that this is equal to this? So how could I do that? Well, if I expand this expression out, what do I get? I get 1/2 x transpose hx, right? It's a quadratic term from here. Plus, I get 1/2 x naught transpose h x naught, right? That's the second quadratic term. And then I get the cross terms, right? And what are the cross terms? The cross terms are just x transpose h x naught, right? And I get two of them, but I have the half, so it cancels. Right? I'm just doing multiplication here. And then I have this plus alpha. Everyone clear on that? Okay. So now, if I just do pattern matching, well, the quadratic terms match, right? What about the constant terms? What are the two constant terms here? What are the terms that don't depend on x? Well, it's this one, right? X naught is a constant, and alpha is a constant. And what is the constant term up here? It's just d. So if these two things are equal, then d had better be equal to 1/2 x naught transpose h x naught plus alpha. And then that leaves the linear terms to be equated. So what do I have here? I have c transpose x, and here I have x transpose h x naught. So what had better be equal? What is c transpose equal to? So I have x transpose c is equal to minus x transpose h x naught, and so I have c is equal to minus h x naught, right? Everyone with me? But what's the nice thing here? H is symmetric, right? So I can write this as minus h x naught. Everyone with me? Good? Okay. So now I had a key assumption here, right? I had said, let me assume that c is in the range of h. And why did I make this assumption when I was making my cases? Because now I want to be able to say that c can be written as minus h x naught. If it was impossible to write c, like I need to find x naught, right? I want to say that I can write f of x in this form. So it's on me to find x naught and on me to find alpha, right? But when can I solve this equation and find an x naught? I can only do that if c was in the range of h, right? Otherwise, such an x naught might not exist. So by making that assumption, I'm saying, oh, look, I can find such an x naught. And once I find that x naught, I can plug it into here, and therefore I can find alpha in terms of d. Okay? So that's why I'm making that assumption. It wasn't kind of completely arbitrary. Okay? So therefore exists x naught such that C. Okay? Now, how do I find this x naught? It exists, but how do I find it? When I have this equation. Everyone's taken the linear algebra class, right? Okay. You want to take an inverse. Can you always take an inverse? Is h going to be invertible? H may or may not be invertible, right? So we have basically two cases. If h is invertible, then x naught is equal to minus h inverse c, right? And then we have the case of if h is not invertible, and I'm going to talk about this in a minute, just hold that thought. But I want to first kind of talk about the case where h is invertible, okay? So now when h is invertible, I can find this x naught, okay? So now I know my f of x is this expression here. When I look at this expression now, I know x naught, and I know exactly what alpha is. I want to now minimize this. And I get to choose, what do I get to choose when I'm minimizing? X, okay? So no matter what I choose x to be, does alpha change? Nope. So the best I can do is minimize this part, right? Because no matter what I do, alpha is still alpha. If I choose x equal to 0, alpha is still equal to alpha. I choose x equal to 100, alpha is still equal to alpha. So what do I want to choose x to be if I was to minimize this thing?
X naught.
X naught. Why?
0.
If I choose x equal to x naught, this is 0. Why can I not make this negative? H is PSD, right? So the smallest this could ever be is 0. Okay? So this is where I'm trying to show this completing the square kind of technique, right? Where I've taken the function, I've broken it up into two things, one of which I say, look, x doesn't affect this guy. The only thing it affects is this, and the smallest this could ever be is 0. So make it 0, right? That's your minimizer. I could have arrived at the same solution by taking the gradient, but this is a different technique and a different way of thinking about the problem. Okay? Everyone with me? So this, what we're doing, so therefore, once we have x naught, choose x equal to x naught as right? Clear to everyone? Okay. Now comes the case, any questions about this? Okay, now comes the case of what if h is not invertible, right? If h is not invertible, then basically any x naught such that right, any solution to this equation will exist. If h is not invertible, what is a guaranteed way to find a solution to this linear equation? Okay, pseudo-inverse is exactly the way, right? Otherwise, you can always fall back to the tried and tested Gaussian elimination. Still works. Okay? And why do we know that there's going to be a solution? Why do we know that we're not going to end up in the case with no solution? Because we've assumed that C belongs to the range, right? So we know we're not going to end up in that solution. And so the way to do this is to use the pseudo-inverse of H. Okay? Everyone with me? We're good? Okay. So I trust that from this you know exactly how I'm not going to go out and compute what P star is for you, right? But you can plug in presumably x naught is equal to H inverse C and compute out the optimal solution for the invertible case, or you can plug in kind of, in this case, I guess, x naught would be minus H plus C, where H plus is now the pseudo-inverse, right? And remember, what is the definition of the pseudo-inverse? Just to remind everyone. How do we define the pseudo-inverse? This is always basically in terms of the SVD, right? The easiest way to define it. So if I have H is equal to U, let's say, and I kind of separate out my sigma matrix into sigma 1, which is all of the non-zero singular values, and then I put 0 matrices everywhere else, right? Because I know that in this case I have some 0 eigenvalues or 0 singular values. In this case, what is my H plus? Well, it's just equal to V inverse 0, 0, 0, and then U transpose, right? Okay, so this you all know. You're comfortable with this. I'm not going to do the algebra on this that much more in the interest of time. We're good? Excellent. So now, of course, there comes the next case, right? We did case 1. What is case 2 going to be? There's two cases. Like, what are the other things that we haven't done? H, what if H is not PSD, right? And then what's the other case that's remaining? H is PSD, but C is not in the range, right? Which one do you want to do first? Does not PSD mean negative semi-definite? Right? So be very, very, very careful about how you use terminology. Okay? So, okay, let's do the case where H is not positive semi-definite. Okay? If, yes?
Is C still in the range of H, or?
No, right now, remember, so how do you negate things that have two clauses, right? Now, this is an AND negation. So basically, the cases that remain, H is either positive semi-definite or not. That's one tree. If it's positive semi-definite, then C is either in the range or not in the range. So you don't have to consider the C range issue, right? Because you're just saying negative semi-definite here. Do you see that? Like, this is like just the negation of that clause is not that C is not relevant here.
Wait, but do we have a case where H is not PSD and C is not in the range?
It's not relevant whether C is in the range or not. Remember, how are we making these cases? This is a tree, right? So H, it's either PSD or not PSD. If it's PSD, we made the case C belongs to range of H, or C does not belong to range of H. So here we're considering this case in general. We're not breaking it. We don't have to break it into two cases. We could if we wanted to, but it's not relevant to the way we're going to do this. So let's think about this now. What happens if H is not positive semi-definite? What does that mean? Our function is not convex. Very good. What does that mean? Yeah. It has at least one negative value. Okay, so just to kind of bring your brains back from spring break, now that you know this, see what you can do. What is the minimizer of f(x)? I'll give you a minute to think. Okay, so what's one thing you want to write on your paper now that you have this? Just speak it out. We don't need to raise hands. Just be informal.
Corresponding eigenvector.
Okay, so what do we have? So we have h times some eigenvector v is equal to lambda times v, and lambda is strictly less than 0, right? Okay. So now where might you try to find, so you have one special vector, v. This has been given to you. So if you want to try and play with your function, where would you try to evaluate your function?
The one with the smallest eigenvalue.
The one with the smallest eigenvalue, but just one negative, right? It doesn't matter which one. But can I evaluate my f at that v, right? So what happens if I consider f of v? What do I get? Well, I have minus 1/2 v transpose hv plus c transpose v plus d. Okay. Good. So how can I simplify this? So how many people, everyone wrote this down, right? How many people went from this to this? You don't have to raise your hand. I just want you to think about this, right? So why did we go from here to here? I'm trying to particularly have this conversation after, questions I've gotten in office hours after the midterm, right? How do you unstick yourself, right? This is a little bit of a leap of faith, right? This is the thing that kind of obviously you have to write. This is the little bit leap of faith. And when I say write something down, write anything down, these are the kinds of leaps of faith that I want you to make, right? You do not know what is going to happen by evaluating f at some random vector. But that's all you got, You have one eigenvalue that's negative. It gave you a vector. Just try evaluating, see what happens, okay? So when I try a simpler problem, write something down, anything down, that's the kind of thing that I'm hoping that you will get to kind of make these leaps of faith, even if you don't know if it's the right step or not, okay? I don't know that this is the right step right now, but this is all I have, so I'm trying something, okay? So I have this now. Let's try to play with it. So now I know h times v is what? Lambda, and I know lambda is negative, so I have this 1/2 lambda norm v squared, right? Plus c transpose v plus d. This is some value of f, okay? What could I try to do? How could I try to make this even smaller, okay? What could I try to play with this? So I know that I can pull this lambda out. So this term now is negative. When I have a quadratic equation in general, right, what is the most important coefficient in terms of telling me whether this thing is going to go to plus infinity or minus infinity? The coefficient of the quadratic term, the leading coefficient, right? So if I have something with a leading coefficient that's negative, eventually if I choose my x large enough in some direction, I'm going to go to negative infinity, right? So here you have something, this is the quadratic term, this is the linear term, and you have something that is negative here, right? You have a way of getting a negative thing. So how could you force it to become, you're trying to minimize this thing, how could you force it to become smaller and smaller and smaller? Okay, now everyone who hasn't done this yet, hasn't figured out the solution yet, now take 30 more seconds. So what did you write down? We evaluated here at f of v. If I wanted to make this more and more and more negative, what could I do? Okay, So I want to make this thing bigger, right? So how else could I evaluate this thing? So what's the next thing you want to try evaluating, right? We tried f of v, but we can't necessarily say that this is the minimum in any way, right? There's no conceivable, this is just some real number. How do I know that it's the minimum? I know it has some negative lambda in it, but so what? How could I make this more negative than it is right now? By my choice of x, I can never really affect this, right? The only thing I can really hope is to try and drive this more and more negative. So what if I considered different multiples of v, right? When we have our negative parabola, you want to get your x to go to either plus infinity or minus infinity. So what multiple of v do you want to consider? If I consider f of some k times v, okay? K is some real number. What is that equal to? 1/2 kv h, kv transpose, sorry, kv plus kc transpose v plus d, which is equal to now 1/2 k squared lambda okay? So here, what are you observing here as I evaluate this kv? Does it really matter if k is positive or negative? In the leading coefficient, what is this leading coefficient here? This is always negative. K squared is always positive. Norm v squared is always positive. 1/2 is positive. So this whole thing, because of its lambda, is negative. So your leading term, your quadratic term, is negative. So now, what do you want to do to k to make sure that this whole expression is negative? Take k to infinity, right? As k goes to infinity, only the quadratic term matters. And so, f of kv, what does f of kv go to as k goes to infinity? Goes to negative infinity. So what is the minimizer, or what is the minimum of f of x? What is p star? Negative infinity, right? And how do you find that negative? What will attain it? Well, it will be some multiple of that eigenvector with the negative eigenvalue. Once you get large enough, it's going to go to negative infinity. Okay? Yes, question?
Do we also have k go to negative infinity?
K could also go to negative infinity, and it would still, the whole thing would also still go to, because again, remember, parabolas have this shape, right? They can go to infinity in multiple directions. And in this case, again, your quadratic term would still go to negative infinity. And the linear and the constant term aren't going to matter when you're taking the limit. Yes?
If you have multiple negative eigenvalues, does it matter which one?
Question is, if you had multiple negative eigenvalues, does it matter which one you choose? No, there's multiple ways to attain that negative infinity, right? If you had a negative semi-definite h, this would still hold. If you had only one negative eigenvalue, this would still hold. It doesn't matter, right? Because here, does it matter which one we chose? Not at all. Okay? Good. So now, what's the case that remains? Okay? So this completing the square trick is now somehow not going to work, right? So now, okay, let's think through this again. How do you think about solving this? How do we get from here? So now if this was on an exam, right? Or, you know, more importantly, if you're like trying to build something, if you're trying to optimize a function in your first job after you graduate, how do you start? That's not, let's type this into Google and see what Google says. Sorry, yeah, ask ChatGPT, sorry. Roll with the times, right? Yeah, when I was an undergrad, like you couldn't even type into Google to see if Google knew the answer. Like Google was still very new. I got one of the invite-only Gmail accounts. That's how Google was. Yeah. Okay. So how are we gonna handle this? You could try to use the gradient, but I want you to try and think, what do we know? So we have H is PSD, and we have now C is not in the range, okay? What things do we know about the range of H? What is the one, how much do we know about the range of H? What are the things we know when we talk about the range of H? What are connected things? Just shout out things. There's null space, okay, fundamental theorem, right? So if it's not in the range, what do you know about, what does the fundamental theorem tell you? That the range space of H plus direct sum with the null space of H transpose is your full space, right? So if it's not in the range, what does that mean? Does it mean that it's in null space? Not quite, right? It has at least a component in the null space, right? It could have a component in both, but at least it has some component, right? So it means that C is equal to, okay, so again, the first key thing, right? Write something down. So you see this, you say, let me dig out of my brain everything I know connected to range space. You got to write this down, right? If you don't write this down, it's kind of hard to get to the next step. Does everyone see that? So that's why I keep emphasizing write stuff down. Now you have C. So I want to write something as C as something belonging to this plus something belonging to this, right? So I can write as C is basically H times X naught, right? Something in the range plus some remainder R, where R belongs to the null space of H transpose, right? And in this case, because H is symmetric, this is actually exactly equal to the null space of H, right? We don't have two different matrices. H and H transpose are exactly the same. No, this is now a completely different X naught, right? This is just some X naught, right? Because C does not belong to the range, I can write it this way. If C belonged to the range, this R would be 0. But C does not belong to the range, so now R is not equal to 0, right? The null space is, we're finding a non-zero vector from the null space. Okay? Good. So now, following what we did here, what is something that you might want to try? Okay, if I had to force you now to write something down, what might you want to try writing down? What might you want to try calculating? You have no idea if it's going to work or not. You could decompose something into two parts. Okay, what do you want to decompose? Okay, you could try decomposing. That's definitely a strategy. You could try writing something out like that. I'm thinking about even something simpler. Decomposing requires like coming up with how to decompose.
Let's just substitute C for this expression.
Substitute C for this expression. Okay, that's a good idea. Substituting C. What did we do here? We had H had at least one negative eigenvalue, and then we got some special vector V, right? And then we said, hey, I got to try and evaluate it somewhere. Let me evaluate at V. In this case, do we have such a special vector V? We don't have the V, but what did we get? We got C. But is C that special? C was already given to us, right? We have this property of C. But yeah, I would try evaluating at C. See what happens if you try evaluating at C. What else could you try to evaluate at? R, right? That's the other kind of thing that's out there that's kind of different, right? That is not following, that's not matching the cases that we've done so far. Evaluating at x0 is kind of like the first case we did. So you have some options. Write something down. See what happens. Anything down. So now if I was to try to do this. So evaluating, I could also try to evaluate this at C, right? These are like the two special things. We have C is kind of special, and R is kind of special. A general rule of thumb is also like there's a value to laziness very selectively, right? So laziness does not mean I'm not going to write anything down. I'm going to wait until the perfect equation comes in my head, and then I'm going to write it down. But if I'm deciding between whether to evaluate at f of C first or f of R first, my first term that I'm going to evaluate is 1/2 H transpose X transpose HX, right? Is it particularly easy to evaluate that term for R or C? How convenient, right? To evaluate it at R. Might as well try that first, right? So this kind of selective laziness can also have some value, right? Why bother doing the C calculation? Let's do it for R first. So if I had 1/2 R transpose HR plus C transpose R plus D, what is this equal to? 0, right? And now I can write C transpose R as well. This is just HX0 plus R transpose times R plus D, right? So we're substituting C as you all had suggested. And so this gives me now X0 transpose H transpose R plus R transpose R plus D. D is not a vector. Okay? Laziness strikes again. Do I have to evaluate this thing? Also 0. So this is now equal to R transpose R plus D. Okay? So f of R has given me this. So now I have something that is like this R transpose R. What is R transpose R? It's always going to be non-negative, right? Is that particularly good for me for minimizing or not so good for me for minimizing? It's kind of like a little bit confusing, right? It's not as clean as this was coming out to be. Okay? So how might you now try to modify this? Okay, so this didn't work out. R was a good idea. It worked with our laziness. So what might you try to modify to see if you can get this to give you a predictable value, right? If you wanted to get this to go, what is the one thing that would give you a sure shot minimization? If you get this to go to minus infinity, you've won, right? Basically, right? So how could you push this to go towards minus infinity? Okay, if you tried negative KR or just KR, evaluate it, see what happens. Do KR. It's always easier, I find, to choose something to be a KR and then choose K to be positive or negative. Negative KR sometimes means that you're like keeping track of an extra sign, and that's confusing. So always just choose it to be a scalar multiple, and then choose that scalar to be positive or negative as you need it. Okay, so when I evaluate this at KR, what happens to the first term? Again, my laziness is fully active, right? Again, I don't know how to evaluate this. This is still 0. Now, when I look at this, what is the first term here? H0 x0 times KR is going to give me 0. So this also I don't have to worry about. What do I get here? I get K right? And now, what could I do? What choice of K would drive this to where I want it to go to? Right? So as K goes to negative infinity, f of KR also goes to negative infinity. But you see how this is very different from how we draw the negative infinity in the case of the negative eigenvalue. Right? It's a different kind. That negative infinity came from driving the quadratic term to negative infinity. Okay? This negative infinity is coming because of how C behaves. Right? The quadratic term is just 0. Right? So we have a convex problem where the minimum is negative infinity. This is a convex problem. Well, C is just this. C is what it is. C is this, and I'm evaluating this at KR. Only my X expression substitutes with KR. Right? I don't change this to be a KR. Oh, typo. Okay. So quadratic programs are in general useful. We will have a special lecture that will be dedicated entirely to linear control. And linear control problems, like the one in the project, are quadratic programs, right? There's this very special formulation for control that is called the linear quadratic regulator. And one of the reasons that we formulate costs that way is that because you end up with a quadratic program. So least squares is, for example, a quadratic program, right? Quadratics are basically the nicest thing. That's why anytime you have a cost function, almost always the first thing people try is a quadratic cost, right? Because it's nice, it's differentiable, it has all of these explicit solutions. And so basically, in the case that you have a finite optimizer, you can get the explicit solution. Otherwise, your minimum is basically always going to negative infinity, right? You'll see other examples of quadratic programs kind of throughout the class. Lasso, which we talked about last class, can also be written as a quadratic program, right? And we're going to have an entire lecture dedicated to lasso. So we'll talk again about how to reformulate lasso as a quadratic program then. But remember, we use slack variables to say that, oh, we have this L1 norm, but then we can rewrite it to make it into a quadratic program as well. So there's a lot of value in kind of trying to solve these quadratic programs. The one other thing that I wanted to talk to you about, or I guess two other things. First is that there's one class of problems that extends quadratic programs a little bit, which is called QCQPs, which are quadratically constrained quadratic programs. So instead of here having this linear constraint, you have basically a quadratic objective and a quadratic constraint. And the nice thing is that these can also be solved quite efficiently in many cases. So, for example, if I had P star is equal to min of X transpose HX plus C transpose D, or C transpose X plus D. And then I had constraints such that X transpose, let's say, H1X plus C1 transpose X plus D1 equal to 0. So this could be a quadratic equality constraint. Or I could have X transpose H2X plus C2 transpose X plus D2 equal to or less than or equal to 0.
What happened to the vector signs on those X's?
Oh, I just forgot. Okay? So now I have quadratic objective function and quadratic constraints. So this is a quadratically constrained quadratic program. These are not as easy and nice to solve as kind of the QPs that we just did. You don't have explicit solutions for them. But this is a class of problems that can be solved using what are called interior point methods. Okay? And if we have time, we'll talk about them at the end of lecture, which is basically a way of searching for an optimum using both the primal and the dual aspects of the problem. But these are algorithms that can be implemented efficiently. And this is also true of second-order cone programs, which is what Dhruv is going to talk about on Thursday. So these are also programs where you can use interior point methods to solve them. And so like linear programs, right? Linear programs, one of the things is that we can find explicit solutions for them. But even when finding an explicit solution is hard, the simplex algorithm, which is this greedy approach, basically says the search over the vertices one by one by one will get you to an answer. You have an efficient algorithm that works. That's why we like linear programs. Quadratic programs and second-order cone programs, we can use, either you can find an explicit solution, or if you cannot, you can use interior point methods. So that's why kind of these QCQPs are nice. Of course, these are nice and easy when you have them as convex problems. So you want basically the H's here to be PSD, right? H1 and H2 to all be PSD for these to be convex, and therefore for interior point methods to work well on them. Okay? But we haven't talked about interior point methods, so don't quite worry too much about that. There's one more thing I want to tell you about, which is what is called. So we only talked about unconstrained quadratic programs so far, right? What about if you have a constraint? So if I have an equality constrained, so that means I have such that okay. So now I want to find the minimum of this, but I want to look at over only those x's that satisfy this particular equation. Okay? So that means that my feasible set is given by the set of x such that x is equal to x naught plus, let's say, n times z, where x naught is a solution to ax equal to b, and n is a basis for the null space of A. Right? What are the solutions to this? Well, basically find any particular solution and then add any vector from the null space. Right? So that will always satisfy. Right? If A is wide, it will have multiple solutions. Of course, if A is square and invertible, this will have a unique solution. Otherwise, if B is not in the range of A, this will have no solutions, and then this minimum is obviously not a problem that you're particularly interested in because your feasible set is empty. So the feasible set is non-empty when basically A is wide, right? Or non-unique when A is wide. And so that's when you have an interesting setup here. And so basically what you can do is I can substitute this into here, right? And by doing this, when I substitute this formula into here, what is my optimization? So x naught is something I know, right? What is the parameter here now? What is the unknown here? Z becomes the unknown, okay? But if I say that I'm going to now write this minimization in terms of this, what that does is I say I write this as a minimization over Z now, but I've converted it into an unconstrained quadratic program, right? Because anything that is in this set, anything that satisfies this equation, automatically satisfies the constraint. And so I can write this now as an optimization problem over Z, which is an unconstrained quadratic, and use my previous techniques exactly to solve it. Okay? So the case of equality constrained quadratics, I can reduce to the case of unconstrained quadratic programs. Does that make sense to everyone? Okay, so we will use this when we get to building out how interior point methods work. So keep this in mind. I will not see you Thursday. I will not have office hours, but Dhruv will be giving an excellent lecture. I have office hours today if you want to come talk to me. See you next week.